Ever wondered where stars come from, those twinkling points of light that fill our night sky? Well, the birth of a star is a cosmic event of epic proportions, a testament to the grandeur and intricacy of the universe. Stars, much like life on Earth, are born in nurseries. These celestial nurseries are called nebulae, vast expanses of dust and gas that span light years across the universe. Picture a nebula as a colossal, swirling cloud, a mixture of hydrogen, helium, and heavier elements, all suspended in the vast expanse of space. Over time, pockets within this cloud begin to collapse under their own gravitational pull, a process known as gravitational collapse. This collapse creates a dense, hot core called a protostar. Now, a protostar is a star in its infancy. It's much like a caterpillar in a cocoon, undergoing a metamorphosis. Inside the protostar, the temperature and pressure are so intense that hydrogen atoms begin to fuse together to form helium. This process, known as nuclear fusion, releases an enormous amount of energy. This energy pushes outward, countering the inward pull of gravity. It's a delicate balance, a cosmic tug of war. As long as this balance is maintained, the protostar continues to grow and mature. Over millions of years, the protostar continues to contract and heat up, the pressure and temperature rising until the conditions are just right. And then, in a brilliant burst of light and energy, the protostar ignites, officially becoming a main sequence star. A main sequence star is a fully mature star, like our own sun. It's a cosmic powerhouse, generating light and heat through the process of nuclear fusion. So every star we see in the sky has had its beginnings in a humble cloud of dust and gas, a testament to the incredible transformations that occur in our universe. From nebulous beginnings to dazzling maturity, the birth of a star is a cosmic journey of transformation and endurance. What happens once a star has been born? How does it live out its cosmic life? To answer those questions, let's delve into the life of a star. Once a star is born, it enters a long, stable period, often spanning billions of years. Here it burns hydrogen to produce helium in its core, a process known as nuclear fusion. This isn't just any old chemical reaction, but a powerful process that releases an enormous amount of energy. This energy radiates outwards, causing the star to shine brilliantly in the vast darkness of space. Think of a star as a cosmic powerhouse, with nuclear fusion acting as the engine that drives it. This fusion process is incredibly efficient. A single gram of hydrogen can produce enough energy to power a city for a week. So you can imagine the tremendous energy a star creates, considering it's made up mostly of hydrogen. Now, have you ever wondered why stars come in different sizes, colors, and temperatures? Well, that's largely a matter of mass. The mass of a star determines its destiny. Stars with greater mass burn hotter and brighter, but they also burn their fuel more quickly. They're the cosmic equivalent of the hare in the race against the tortoise, fast and furious, but their lives are typically shorter. On the other end of the spectrum, smaller stars burn their fuel more slowly. They may not shine as brightly, but they are the long-distance runners of the cosmos, their lives extending over tens to hundreds of billions of years. But no matter the size, every star's life is a constant struggle against one foe: gravity. You see, gravity constantly tries to pull a star's matter inward, causing it to collapse. However, the outward pressure created by the energy from nuclear fusion counteracts this inward pull. It's this delicate balance that allows a star to shine for billions of years. So, a star's life is a constant battle against gravity, a battle fueled by the energy from nuclear fusion. What happens when a star exhausts its nuclear fuel? How does it meet its end? These are questions that have fascinated astronomers for centuries. The answer, it turns out, depends on the mass of the star. Smaller stars, like our very own sun, go through a fascinating transformation. As they burn through their nuclear fuel, they begin to swell, morphing into what is known as a red giant. This phase is like a star's retirement. It's run its course and now it's taking it easy, growing larger and cooler. But this retirement isn't a quiet one. As the star cools, it begins to shed its outer layers, casting them off into space. This expulsion forms a beautiful, glowing shell of gas and dust known as a planetary nebula. What remains of the star is a dense, hot core called a white dwarf, which will slowly cool over billions of years. But what about larger stars? Their fate is a bit more dramatic. These stars don't just swell and cool, they go out with a bang. When a large star exhausts its nuclear fuel, it collapses under its own gravity, then rebounds in a spectacular explosion known as a supernova. One such star that may soon meet this explosive end is Betelgeuse, one of the brightest stars in our night sky. This red supergiant has been showing signs of instability, leading astronomers to believe that it could go supernova within our lifetime. If it does, it will outshine the moon and be visible even during the day. The remnants of these supernovae can form neutron stars, incredibly dense objects with masses up to twice that of the sun, but packed into a sphere only about 10 miles in diameter. If the star is massive enough, it might even collapse into a black hole, an object with gravity so strong that nothing, not even light, can escape. In death, stars give life to new star-forming regions, continuing the cycle of stellar evolution. So the death of a star isn't just an end, it's also a beginning, a crucial part of the cosmic cycle of birth, death, and rebirth. How did our solar system form, and what about Jupiter, the largest planet, which almost became a star? We find answers to these questions in the solar nebula theory, which paints a picture of our solar system's birth about 4.5 billion years ago. Picture a vast spinning cloud of gas and dust, a nebula, in the cold reaches of space. As gravity pulls this cloud inward, a dense, hot core forms in the center, eventually igniting to become our sun. But what about the remainder of the nebula? Well, it doesn't just disappear. Instead, it flattens into a spinning disk of material around the newborn sun, a formation known as the solar nebula. Within this disk, solid particles start to collide and stick together, gradually forming planetesimals, the building blocks of planets. Now enter Jupiter. Being the largest planet, it started forming early and grew rapidly, gathering more and more of the nebula's material. Its size allowed it to pull in not just rock and metal but also lighter gases like hydrogen and helium, which smaller planets couldn't hold on to. Jupiter became so massive that it almost crossed the threshold to become a star. You see, stars ignite when their cores are hot and dense enough to fuse hydrogen atoms into helium in a process called nuclear fusion. Jupiter almost reached this point, but it fell just short. It needed about 75 times more mass to trigger fusion and shine like a star. So, why didn't Jupiter become a star? Simply put, there wasn't enough material left in the nebula for it to gather. The Sun, being closer to the center of the nebula, had already claimed the lion's share of the available matter, leaving Jupiter as a failed star, or more affectionately, a gas giant. So, Jupiter is a testament to the thin line between a star and a planet, and a reminder of the incredible diversity of objects in our universe. This gas giant is a fascinating example of how the universe is full of almosts, and how even in failure there can be spectacular success. What have we learned about the life cycle of stars? We've embarked on a cosmic journey, spanning the birth, life, and death of stars. We've seen how stars are born, nurtured in the celestial cradles known as nebulae. These are vast, colorful clouds of gas and dust where gravity pulls matter together to form a protostar. Over time, as the protostar gains mass and heat, nuclear fusion begins, marking the birth of a new star. Throughout their lives, stars burn hydrogen in their cores, radiating energy and light into the universe. The size and mass of a star dictate its lifespan, with larger stars burning through their fuel more rapidly, living fast and dying young. Smaller stars, on the other hand, can burn for billions of years, shining steadily and consistently, much like our own sun. The death of a star, though it may sound grim, is a spectacle of cosmic proportions. Depending on their mass, stars meet their end in a variety of ways. Some gently fade away as white dwarfs, their nuclear fires extinguished, leaving behind a glowing ember in the darkness of space. Others, more massive stars, end their lives in a violent supernova explosion, outshining entire galaxies for a brief moment before collapsing into a dense neutron star or a mysterious black hole. We've also learned about the supernova of Betelgeuse, a prime example of a star reaching the end of its life cycle, and the formation of neutron stars, incredibly dense objects born from the remnants of massive stars. Our journey also took us closer to home, to the solar nebula from which our own solar system was born. We saw how Jupiter, the largest planet in our solar system, failed to ignite its nuclear fires, becoming a failed star, a gas giant rather than a sun. The next time you look up at the night sky, remember each twinkling star has a story to tell. A story of birth, life, and death played out over millions of years.